This is Premier Aerodynamics Podcast number 28, and today we're talking about whether morphing wings are any good or not. So to look at this, we're going to look at a paper called Aerodynamic Investigation of a Morphing Wing for Micro-Air Vehicle by Means of PIV. So morphing wings is exactly what it sounds like. You have a regular wing, but it can change its shape. So whether that's camber or thickness, or even rotating, or you can wash in or wash out. So you can change it depending on the flow and what you need it to do. And the question is, are they any good? Because they are effectively an active flow control device. And when they become active, it means you have to use energy to change it, and that can result in being less efficient sometimes, and also potentially can break easier. But if you get it right, then it can become a lot more efficient, and it can be robust if you do it well. So let's look into whether morphing wings actually have any aerodynamic benefits. In the abstract, they say due to the low aspect ratio of the wing and the low Reynolds number that they tested, the influence of the 3D effects has been proved to be important. At high angles of attack, the modified model prevented the detachment of the stream, increasing the lift of the wing and reducing the turbulence intensity on the upper surface of the airfoil and in the wake. So in other words, at the Reynolds number that they tested, which was 64,000, they found that their morphing wing did greatly benefit the lift of the wing, so it and also delayed stall, as we'll look at later in. So let's look into the details of this paper now that we know that there is some benefits to a morphing wing if you do it properly. They start to introduce the topic. They say the idea of changing the wing shape or geometry in an aircraft to adapt to each aerodynamic condition of a typical mission profile is inspired by the observation of flight in nature and is far from new. So I'm guessing that they mean birds and insects, which they do change, whether their tails change a little bit of geometry or whether they pitch their wings a little bit differently, whether they put their wings at a dihedral angle. For example, pigeons, if you ever look at a pigeon landing, just look at how it puts its wings. It goes in this V shape. And the reason why they do this is because it does still produce lift, but it makes the pigeon very stable. So even if they do have gusts coming along as they're landing, they're not really phased by it. They can still land very easily in this configuration. Also, their tail spreads out a little bit to help them achieve a bit more control. So morphing a lifting surface is not that new in the animal kingdom. It's just new to us human animals. So the wing that they looked at, they had a wing planform which corresponds to a Zimmermann wing type, which consists of two half ellipsoids joined at 25 and 75% of the chord. The planform wing has an aspect ratio of 2.3, and it is very efficient by its nature. So they have a picture here which shows the Zimmermann type wing. For those of you listening to this, what it is effectively, think of having two ellipses, one which is has a very high aspect ratio, so it's very oval, the other one which is much more circular. They got the oval one and they cut it in half along the lengthways, and then they stitched that to the other half of the other ellipse effectively, and then they make an entire wing. And the sharper side is on the leading edge and the more circular side is on the trailing edge. So that's how they made the Zimmermann wing. They go on and say the profile of the unmodified wing was an Epler 61 profile. So the Epler 61 profile, if you're not familiar with that, is a curved and it's a cambered wing. It's fairly thin, but it's got quite high camber, so it has non-zero lift at 0 degrees angle of attack. They say that the actuators were installed in the cavity of the intrados at 40% of the chord, and 4 modified configurations were defined depending on the voltage applied to the material. So let's discuss how they did this. So how do you make a morphing wing? There are a few different methods, but one of the most common is you use a material which is sensitive to electricity. So once you apply a current through the material, it will then it will shrink and it will get tenser, and then it will change shape. And this is what they had here. They had something called a macro. It's a proprietary piece of equipment. It was called a macro component, and what this does is it's effectively like a piezoelectric component. So when you put a voltage through it, it shrinks and it contracts, and then you can get a change in shape of the airfoil. So that's how they made this. And they have the morphing models here, and they have some pictures of it, and they had a half model. So they didn't put the entire like little aircraft with the two wings. They just cut it in half and they stitched it to the wall. And to give you an idea of what it looks like, it kind of looks like a half sparrow. So if you get a sparrow and you get it halfway like down the middle, the left half is what this looks like. And when they change the shape of the wing, you can notice that the trailing edge seems to be quite a bit more drooped than the non-modified version. So it does work quite well, it looks like. Now, one thing that's interesting is the wind tunnel that they used. So this thing is tiny. It has a mean aerodynamic chord of less than 10 centimeters, 9.35, which is very small. So it's like 4 inches. And the wind tunnel that they used had a test section of a 3 meters by 2 meter cross section. So it's huge compared to this little thing. So the blockage ratio would be like 0.001%. Is nothing, which is what you want, but most people don't have the cash to be able to run such a small model in such a big wind tunnel. But obviously these people do, so good on them. So going on to the results, they looked at the lift of this little thing. Before we go any further, I just want to talk about Aerodynamics. So check out all the instruments we make here at Aerodynamics. We make PIV systems, traversers, and the Atmosphere Hawk. Check them out, link in the description. Check out the courses we put on to make you a better analysis. We do CFD, theoretical, and experimental. And check out the International Aerodynamics Conference, which is a conference we put on every year for aerodynamicists to get together and talk about aerodynamics. All those links can be found in the description. So onto the results. They found that when they're looking at the modified version, they said that it is also observed that the velocities found in the modified model are greater than the original model. So the flow going over the wing has accelerated more. And this resulted in an increase in lift. The lift, and what they have here are some values, and compared to the Epler 61, which is the unmodified version, the modified version greatly increases lift. So just to give you an idea, at 0 degrees angle of attack, the lift coefficient of the Epler 61 is 0.19, compared to the modified one, which is 0.31. So it's a 35% increase in lift. Actually, more, it's 50% increase in lift overall. The drag was also lower at 0 degrees angle of attack. So for the Epler, the drag coefficient was 0.102. For the modified version, it was 0.075. So a 25% reduction. So it's massively improved this performance at 0 degrees angle of attack. Now, when you go to 5 degrees angle of attack, the lift still is much higher. So for the Epler, it's 0.42 compared to the modified of 0.67. So again, 50% more. But the drag now has jumped up a lot. And it's now higher than the original version. And this remains the case for all the additional angles of attack effectively. The drag is always a little bit higher. Sometimes it's a lot higher. Sometimes it's a little bit higher, or about equal. But the lift is always about 50% more for the modified version, which is impressive. And one thing that's very impressive is at 20 degrees, the Epler 61 seems to have its maximum lift coefficient of 1.11. But the modified version doesn't reach its maximum lift coefficient until 25 degrees, at least. Now, they only tested up to 25 degrees, so it could be higher, and you could get a higher lift coefficient. But at 25 degrees, the maximum lift coefficient was 1.54, so much more. So this shows that modifying the wing does greatly improve the aerodynamics of the aircraft. So not only at certain angles of attack does the drag drop, but at all angles of attack, the lift increased. So this means the lift-to-drag ratio, which is a measure of the aircraft's efficiency, dramatically increased for all angles of attack they considered. So in conclusion, they said that it is also concluded from the rest of the comparisons that the modified model increases the lift of the wing and reduces the turbulence intensity level on the upper surface of the airfoil and in the wake. So the turbulence intensity level, this is interesting because it applies to whether the flow is turbulent or not. So it's going to affect the critical Mach number, which is sorry, not the critical Mach number, the critical Reynolds number, which is effectively the point where the flow transitions from laminar to turbulent. So the transition region is going to push it higher. If you have a lower turbulence intensity, you're generally going to be able to go at a higher Reynolds number and still have a laminar flow over the rest of the wing. Whereas if you have a high turbulence intensity, you're going to get that transition at a much lower Reynolds number. So that has some ramifications for not only skin friction drag, but also pressure drag based on flow separation characteristics and whether you get laminar separation bubbles and this and that. So that's one thing that's actually quite interesting with this morphing model, because they said that it reduces the turbulence intensity level on the upper surface, this is probably going to be more conducive to laminar separation bubble formation. The reason why is because laminar separation bubbles really form when you have small disturbances which then grow. And so this is ideal for this. What that means is in certain Reynolds numbers, you're probably going to get a fairly inconsistent lift coefficient depending on like what you're doing with the aircraft. If you just go from 0 degrees to 10 degrees, you get one type of laminar separation bubble formation. When you go from 10 degrees to 0 degrees, so the other way, the hysteresis is a massive problem. So it can have an effect on laminar separation bubble formation. So that's one thing that would be interesting to look at with this. And finally, they say, we conclude that morphing wing configurations provide an augmentation on the global aircraft performance, mainly at high angles of attack. So I thought this paper was pretty interesting. The link is in the description for you if you want to look at it. It's open access. Make sure to like and subscribe to this. Check out everything we do at Aerodynamics. Check out the instrumentation we do. Check out the courses we do. And check out the International Aerodynamics conference we put on. And I'll see you in the next podcast. Peace out.